Hi everyone, welcome back. I hope you watched the last tutorial where I provided a quick introduction to Detectron2 framework, and we have actually used a couple of pre-trained models to segment a natural scene image where we looked at individual cars that got segmented and individual humans. But as scientists and researchers, we have our own images to work with. For example, you see an image of a bunch of cells with some organelles that got segmented on the right hand side. Again, I did that. Literally, this is the goal for today's video, where we try to achieve the right hand side and of course quantify it and get some area measurements and so on. So how did we do that? That's the whole point of this video, going from taking the images and annotating them, loading them onto our Google Colab for Detectron2 based image segmentation or instant segmentation using mask or CNN as the engine that kind of powers up the whole thing. And if you don't know what I'm talking about, please do watch my last video. And if you want to be notified of future videos, just hit the subscribe button right now if you haven't already done so. And while you're there, find the little thanks button if you're feeling extra generous. Okay, so like I summarized, our goal is to just understand this Detectron2. In fact, I have the next slide where we laid out the plan. Step one is to get our training data ready. And for that, there are various ways of annotating your data. You can use whatever your favorite program is, as long as you can get Coco style JSON format annotations. And if you don't have a favorite program, then we can just test this makesense.ai, which is what I ended up using in generating a handful of labels. And then we'll walk through the code in Google Colab to train and of course to segment future images. But first, let's understand the image segmentation challenge, right? I mean, we get hung up on this code all the time. We're like, oh, let's use TensorFlow, let's use PyTorch. Well, if you understand the problem, if you understand your images, what is the image segmentation challenge? Maybe a simple Otsu-based thresholding is enough, right? So what are you trying to achieve from your segmentation? And let's look at the example I'm gonna go through, and you can download this data set, and the link is on the top right bottom. As you can see, Liebman Lab at github.io/dense-cell. So this is cellular segmentation. Even if you're not a biologist, I'm a material scientist. I pretend to be a biologist, but biology images are fascinating because they offer a bit of a challenge if you want to segment them. Although geology and remote sensing, all type, everything is a challenge. I take my statement back there. So the goal here is to segment cells and whatever the subclasses, organelles you can call them. And these are platelets, and they were used using Z.A.S Sigma 3 view by this research group that I'm referencing at the bottom left. Now, how do the images look like? As you can see, these images, I should admit, I downloaded this data set and I converted all 16-bit to 8-bit images. I mean, you don't have to, but I did. And for training, I trained 5 images. Why only 5? I lost my patience after 5 images, and I wanted to see how the results look like. They already look great, but obviously any deep learning, the more training data, the more robust the trained models are going to be. So of all the images that I downloaded they have training set, they have testing set, they have validation set. I just looked at the training set and I took images numbered 1, 11, 21, 31, and 41, and I used those for training, and 2 images numbered 5 and 35, I used them for validation. In case you plan on reproducing exactly what I have done, you can see exactly what I've done here. All other data, I just put it in the test data set, so we can just test it out. The real test is actually taking this training data and applying on the test data set that they have provided, this research group has provided. So this can be a very nice project by itself. If not a master's project, it can definitely be a nice side project if you're doing your bachelor's. Okay. Now, if you look at this image and the corresponding classes that need to be annotated, they have, of course, you have the background. We don't need to annotate the background for instant segmentation, but for the objects itself, you have the cell, which is the entire large area, right? That is the cell. Within each cell, you have different organelles like mitochondria. Unfortunately, you don't have a lot of mitochondria in these. As you can see in this specific image, I have 1, 2, 3 mitochondria in red, or 4 actually. That's pretty much it. and I annotated 5 images. In fact, in 5 images, I got like 12 mitochondria or something. So definitely not enough. So when I segment, I probably expect lower accuracy for mitochondria, but we'll wait and see. And alpha granule are these medium gray blobs that look like mitochondria, but then they are not as dark. So they are like medium gray. And these carnicular vessels, they are this lighter gray blobs. They're represented in green color on the screen. And in addition to that, there are a couple of other regions called the dense granules and dense core, but they are even more rare. I saw them only in a couple of images, so it's not worth for a tutorial to look at that. But in a real life scenario, obviously you're gonna focus on those. So what did I do? I used make sense. Again, we are going to use that right now. And I defined these classes called cell, alpha granule, mitochondria, and carnicular vessel. And then I annotated. Here is the annotations. This is how I kind of annotated. For each image, I just went ahead and used the polygon tool to define around these objects. Again, we're going to do that on one image right now, and then we'll understand exactly what it takes. Now, after you're done with all of these images, then you go back. You hit on export, and I exported them as single file Coco JSON format. That's it. I have done nothing other than that. So we're going to follow that in a second. So let's go ahead and jump to the code. In fact, before jumping to the code, let's jump to this Make Sense web page and upload our images and go ahead and annotate to get a feel for what it looks like to annotate these images for instant segmentation tasks. And of course, the same annotations can be used even for mask or CNN if you want, because it's the same format. Okay, so here we are. This is makesense.ai. I'll leave all the links down as part of the description. And first of all, how do I have my data? So when I downloaded the data, of course, I took, let me go back one step. Let me go back. And here is how I kind of organized it. I have the train directory, test directory, validation directory, and I also created 2 additional directories called test results, because once I segment these test images, I want them to be stored under test results. I will also show you how not to just save these bounding box images and all colorful images, but actually for scientific image purposes. What is the reason why you're doing this? Because you want to, for example, do some downstream analysis, put all these images back together into some sort of a 3D format and then extract certain metrics. I'm just thinking out loud. But whatever it is, you may want your results to be in instance format, meaning you want a binary image only for cells. Another binary image only for mitochondria, and so on, right? So if that is the case, if you want to import this into, I don't know, image J, for example, then this is that's the placeholder. I'll show you how to do that. So in my train, I should have 5 images, like I just showed you, 1, 2, 3, 4, 5. And this is the JSON file I downloaded after annotating them. And same with validation. I have 2 images and the corresponding JSON file. Obviously, for test images, I don't have any ground truth, so I do not have a JSON file, because I don't have time to annotate 50 images for 4 different classes. Yeah, that's the images that I can use for testing purposes. So with this, again, now let's go to Make Sense. I just downloaded like 5 images, the train images. I have them accessible here, but let's go ahead and hit Get Started down here. And now click here to select or drop images. So let's go ahead and drop all of these 5 images right here. Okay. And now we need to pick a task. Is it image recognition? No, we're not classifying the entire image. We are actually doing object detection. Let's click on object detection. Now let's go ahead and define our classes. What did I call them? Cells. And another one is mitochondria. And another one is, I think, alpha granule. Yeah. And the next one is carnicular vessel. Okay. Let's not worry if the spellings are right or wrong. If you don't like a specific color, I think you can cycle through them. If you don't like yellow, hey, it's tough to see, you can just click on it. You'll cycle through like different colors. So go ahead and do that. And now you're going to start the project. Okay, now we are all set to go ahead and annotate them, and you can pick which ones to annotate. Let's say we are annotating the mitochondria. This is where I looked at the ground truth that these guys actually provided, and then looking at that, I'm annotating these. And I found these crosshairs to be irritating, so I turned the crosshairs off right there, and now you only have this. And now you can go ahead and zoom in and use the click and drag thing, click and drag. This is how I start. Top left, I go down, and then I go down, and so on. Now let me turn this tool off, and just with this, on the right hand side, instead of point line, I'm going to select polygon right here. And now let's go ahead, and you should be a bit more careful, but I think I'm not doing a bad job right there. And as you can see, there you go, and click back on the first one so it closes it up. Now, what label do you want to provide? This is a mitochondria, so let's go ahead and select mitochondria. Right? Now, let's do one more. I don't know if this is mitochondria, but it looks like it. Yeah, this one is mitochondria, right? So I'll go back, and I will annotate all mitochondria first, because I don't want to switch between different classes when I am annotating. That's not an efficient way. So let's go ahead and define this. It automatically adds that to mitochondria unless you change it. So let's say you're done with this image with all mitochondria. You just click on the next one and go ahead and continue the process. So let's do this one more time so I can show you. And now I am going to draw, click, 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 click. And there you go. And it automatically adds that as mitochondria. Now you do that for all the images. Now I go back to the first one, and now I am going to zoom. Well, let's zoom out because I would like to do the cells. So let's actually add this as a cell. I recommend you to add cell the last, because once you do that, it covers the entire cell, and it makes it a bit challenging for you to see the stuff that's inside, because now we have classes inside another class, right? So let's leave this right there, right there, right there, right there, and there you go, and adds a cell. You know what I mean now, but it calls this mitochondria, right? So let's change this to cells, and there, that is a cell. Let's add another cell now. So let's add this one. And it should stick with the cells label. I'm going to be sloppy right now so I can make the point, but let's do that. And you see how it adds this as cell. So unless you change it, it's going to keep continuing with that label. That's why you need to be a bit careful when you're switching from one to the other. This is exactly why I recommend doing all the class 1, like mitochondria, for example, first, come back and do all the other one, and then come back and do all the other. And once you're done, you go to actions and export annotations. And this is where select Cocoa JSON format and export, and it exports, well, let's click on it. It exports a JSON file, as you can see, and that is exactly the file that I placed along with my train images right here. And this is exactly the JSON file. That's it. Other than that, I have done nothing. Now you know how to get started with your annotations. Now let's go ahead and look at the code. Let me zoom in a little bit to make it easy for everyone to see. I hope you can still read it, but zooming it a lot makes it challenging to, sometimes it can be too big, but that's fine. Okay, so this is Google Colab. I've already connected that to my drive. As you can see on the left hand side under my drive, I have Colab notebooks, and I have my data, and I have my 3D EM platelet data. I have test all the same structure that I showed you. In addition to this, I also have a placeholder in models called Detectron2 _models, so I can save any of the models under models right here. Okay, so that is that. I can close this part, and now let's go ahead and walk through the code. And runtime, no need to mention, change the runtime to GPU, because we do need GPU in this case on Google Colab. Okay, so now let's start by installing Detectron2. In the last video, we actually did go through this exercise. So this is the code that makes it easy to install Detectron2 on Google Colab. But if you are installing it locally, then it's just pip install and go ahead and do this git.git. Okay, so obviously don't do both. You don't want to overwrite and you don't want to confuse the system. But we are installing PyYAML. and also Detectron2 somewhere down here. Yeah, we are cloning the Detectron2 repo right here, and we are running the setup. Just copy and paste this code, so it should work right away. And after that is done, we are going to import PyTorch, because Detectron2 is based on Torch, and we are also importing Detectron2. And let's go ahead and print out the versions of Torch, Detectron, and what CUDA version we are using and all that. So it makes it easy for you if you're watching this video 2 years from now. I don't know. This is August of 2023. So hopefully this video is still relevant based on when you're watching it. But anyway, the Torch version is 2.0, CUDA 11.8, as you can see, and Detectron is 0.6. With that done, let's now get actually into the meat of it. I am importing Detectron2, and we are importing all the required libraries and model zoo, because we are going to experiment with a pre-trained model initially and then jump into training our own custom model. I promise I don't waste too much time. This is for those of you who did not watch my previous video, but still, I just want to make sure we are on the same page. And default predictor, get config, we'll talk about these once we get to that specific cell, but let's go ahead and import the required methods here. Okay, so the default models are trained on natural images with a whole bunch of classes. In fact, let me go to edit, clear all outputs so we don't see anything, because obviously I did test my code. It's working, but I don't want you to be distracted with all the previous outputs. Okay, so I already downloaded an image called kitchen.jpg, and I placed it under my drive here, and I am going to run it so we can see exactly what that image looks like. Again, I zoomed in a lot so you see this image as humongous, but you get the idea. There is a whole bunch of stuff going on here, including this semi-transparent glasses, and there is some stuff in here. So let's see if pre-trained models actually do a good job. How do you do that? We need to instantiate our config file, our configuration, and you do that using this getConfig method. This is one of the things we imported from Detectron2, and I labeled it config, CFG. Now go ahead and get the model, the structure of the model, which is mask RCNN R50 right there. So this is the model that we are adding to our configuration file, and then I'm setting the threshold to 0.5. And threshold is basically, hey, there is a, let's say, 60% probability that this is a chair. Then if the threshold is 0.5, yes, it is a chair. But if there is 40% probability, then this threshold is not going to let that happen, right? So that's what the threshold is. And here we just got the models. We need to fill the weights in the models. Instead of random weights, we need to fill that with the pre-trained weights. That's what this step does. Excuse me. And we are creating a predictor object using the default predictor method that gets applied onto the configuration file that we just created, or to the configuration settings that we just created. And we can use the predictor method on a image, which is what we are doing here, right? Our IM is nothing but this image, and that's what the output is. So let's go ahead and run this bunch of code. And once we get that, let's go ahead and look at how the outputs looks like. And this outputs, again, is a container. It's not just it's a dictionary. It's not just a NumPy array. And what does it contain? It contains the instances, the predictions, and let's go ahead and print out the instances, like both the classes and the boxes. So when you print that out, you can see right there, these are all the class numbers. There's a lot of classes right there, obviously, and these are all the tensors, meaning, you know, the boxes, the bounding boxes. That's not good enough. We need to put those on images. So let's do that as the next step. We are creating a visualizer object by using the visualizer method. And what are we visualizing? The image, and get the metadata out using metadata catalog method, and onto our data set right there. And let's change the scale to 1.0 so the image is not as humongous, maybe even 0.8. Let's just make this 0.8 so the image is small enough, and cv2.imshow. There you go. So that's a potted plant, 79%. This is an oven, 71%. It does an amazing job. Well, that's probably a washer, not an oven. This is an oven. It's uncommon to have a washer in the kitchen, but there you go. That's the oven. This is another. That's a washer. This is a regular washer, I think, or a dryer, and that seems to be a washer, but it calls it an oven. So it's highly confident that it's an oven, but it's not. It's a washer. But anyway, you can see how it can confuse that. But everything else, it does a good job, including these cups inside this cabinet and bottle refrigerator. So it's working fine. It's working great. I have no complaints. If I really care about getting this oven and these right, I'll add more data to customize the training for this one, but that's not our goal. Now, what if the model, that's the natural image, but what if I supply my specific image, which is this one right here, and we just saw that, and how does it segment? So let's go ahead and segment it using the pre-trained models, for instance. Again, we saw this in our last tutorial. It thinks this is a tie, 55%. This is a pizza, 61%. It's very confident that this is a tie. And that's a donut for some reason. Maybe because it sees all these holes and stuff. 50%. Obviously, the point is, pre-trained model is not good for our customized application, so we need to train our own models. So now that I've proven that, we need to train our own custom models. Let's see how we can do that. First thing first, we need to define our data. We need to define our data set, and I am going to register my data here. And the way you do that is from the data sets within Detectron, go ahead and import register Cocoa instances, because our labels are Cocoa labels, and I am going to register Cocoa instances. What am I going to call that? The first one, I'm going to call it my dataset underscore train, and for that, my JSON file is right here. Go ahead and look at the documentation of the register Cocoa instances, but basically you'll see the same thing. Give a name for this data set, and go ahead and tell where the annotations are. The JSON file is the location of it, and go ahead and give the directory name for where the training data is. And I did exactly the same for validation data. That's it. Now that the data sets are registered, now I can actually use my train dataset, my dataset train, my dataset val to extract information. And that's what we are trying to do here. So from my dataset train, go ahead and extract the metadata information. Also go ahead and extract the dataset dictionaries. And there you go. And you can see loaded 5 images in Cocoa format, and it should give you all the right information right there. Let's do the same for our validation data, because we'll need that later on. Yeah, this part is I'm just making sure that, okay, everything is working fine. My data set is registered fine. I'm extracting the information here. And let's go ahead and plot it. Yeah. And now I have these objects, dataset dictionaries, validation metadata, dictionaries for train metadata right there. So let's go ahead and use the train metadata and the dataset dictionary, wherever the dataset dictionary is, train dataset dicts. And let's go ahead and plot 2 images from our training dataset, just to see how they look like. It's not just plotting, it's actually segmenting it using the pre-trained segmenter, which is irrelevant for us anyway, but you can see how it thinks. Sorry, we are not segmenting it here. We are actually visualizing. I take my word back. I should have more coffee right now. And all it's doing is it's drawing the metadata right there. So it has information about our training data, annotations right there. That's exactly what it's drawing. So what I meant to say is, here is where you confirm that your annotations and your images are kind of making sense right now. So part of the annotations in JSON file format, it has the image file name with it, and it has the annotations associated with it. I recommend you to study the JSON file and see how it's storing all the information. So it kind of takes that information and puts it on here, and I have no complaints. You see how it's actually matching the cell, and this is all my annotations. This is what I have done, right? And this is another image where it's actually overlaying all the cells and all the annotations that I have actually performed. As you can tell, I got a bit lazy. I did not annotate all objects. I annotated most of them. So I know my data is loading fine. You know, everything is working okay. Now let's go ahead and get the training ready. Now, how do you train it? Again, you can copy and paste this, but every line makes sense here. So first thing first, let's go ahead and define a configuration. You can use a different config name if you want, but I'm just calling it CFG. using getCFG method right there. First thing first, to this configuration, I want to add an output directory so it knows where to store the models. And remember, I created a directory called Detectron2 models. This is where I want all the models to be saved. And then go ahead and download a model called mask RCNN R50. This is what I'm going to use with random weights for now. Until I tell it to update the weights, it's not going to do that, right? And what training dataset am I going to use? My train dataset. Remember, my dataset train. This is what we just instantiated. Like this is what we did up here, right there. My train dataset. Oh God, there. My train dataset. My dataset train. I keep saying my train dataset. My dataset train. That's exactly what we're going to use to train. You can add testing data. I haven't added that. Maybe I should use the validation dataset right here. But I haven't done that, but you can. And number of workers is number of, this is basically parallel processing. I just leave it to 2. And do you want to use random weights, or do you, meaning start from scratch, or do you want to add some weights? I say, okay, weights, go ahead and get the weights from here, Cocoa instance segmentation, mask RCNN. So it initiates to these weights, which is always a good idea to initiate with, instead of random weights, somewhere in the middle. 2 images per batch, process that. Learning rate, if you want, you can define the learning rate. How many iterations, maximum iterations, 1500. Let's actually change this to, I have trained mine on 1500. Let's change this to 1000. It's not that slow, but still, I don't want to stare at the screen for a long time or pause the video, but let's do 1000. Yeah. Let me change this to 1000. Seems to be good enough for this data set. If you want to step, you can add the delay in the training and batch size. Let's leave it to 256 batch size. And number of classes. In our case, we have 4 classes. This is very important. Do not include background as an additional class. In some cases, I think for mask RCNN, I forgot, like in some cases you define this as 5 because you take 4 classes plus 1. But in our case, we only have 4 classes, right? So we have cells, we have mitochondria, alpha granules, and carnicular vessels, and that's 4 classes. That's it. So 4. And now let's go ahead and make the directory. Which directory do we need to create? The output directory that we just want to save this our train models, well, I'm losing my mind here. So to save our weights, the training weights after the training, and the trainer is default trainer config. Remember, we have to instantiate the trainer with the configuration file we just defined, or configuration settings we just defined. Once the trainer is there, now the last line is resume or load. If the resume equals to false, that means you want to load a pre-trained model if it's available, or start from scratch if there is no pre-trained model is available. That's what this is, and let's go ahead and run it. It should give you the full summary of exactly what's going on. Go through this. But now let's go ahead and start the training process. So the trainer.train starts the training process, and I'll leave this on for at least a few seconds, and then I'll stop recording. I'll continue after the training is done, because let's see how long it takes. It actually gives a very good idea after the first. It tells me it takes about 6 minutes 54 seconds for the entire thing to be done. Estimated time of arrival in about 7 minutes, right? So you can see the total loss and box and so on. Go ahead and look at these. Now you see iteration number 39, and we have to do 1000 such iterations. So like I said, let me pause and then continue as soon as this is done. Okay, so finally it's done, and it said 6 minutes 54 seconds, and it took 7 minutes 23 seconds. So that's pretty close, right? So let's go ahead, and as you can see, the total loss is going down. So it's still going down. And instead of just looking at the numbers, of course, you can go ahead and plot it. And first thing first, let's in fact, I should have moved these up. Let's go ahead and move that cell up. Let's go ahead and look at the training curves in the tensor board, and let's launch it. Of course, you can do this in your local IDE, right? I hope you know how to do that in the local IDE, but no dashboards are active for current data. Well, let's not worry about TensorBoard for now, but I don't know why it didn't work. It was working last night, so I don't want to troubleshoot right now. But go ahead and run these lines and you should see the TensorBoard, or you can actually capture this and do your own plots. It's up to you. But visually you can see that it's still going down. That means it can actually use additional, I don't know, 200, 300, 500 iterations. Now, the first thing first, I want to save this YAML file, the new configuration YAML file. So in case I want to use it later on, because if I want to load it and do future work, again, I may have an example coming up. So let's save this. Now that everything is saved, and by the way, the model itself is saved because I provided it the path where for it to save. So it should be available as part of our drive right there. Again, we gave the path, and let's not worry about it. We're gonna load it in a minute. Okay, so whatever that output directory is, there should be a model underscore final path. In fact, let us confirm that we have the latest model. So what is our output directory? So I have to go back. Sorry, give me a second. So I have to go back. I've got this freaking new mouse that's very loud. I hope it doesn't interfere with this sound here. But okay, under models, Detectron2 models, right? So let's go here. My drive, Colab notebooks, models, Detectron2 models, and there should be the configuration YAML file that I just saved, right? So let's go down. We saved this. Where are we? We are right here. Okay, so this file right there, so config.yaml is right here, you can see, and the model final path, this one, the model underscore final.pth is what we are trying to load right here. So configuration models weights, go ahead and do that. And I'm setting for this new configuration, I'm setting a threshold to be 0.5. This is where you can adjust. And I'm creating a predictor object with the default predictor and configuration as the CFG as the input here. We have done this before, so I hope this is not a surprise to you. We create a predictor object, and this is the object that we apply onto our images. So we get an output, and that output contains the instances and other information about the segmentation, which is what we are using down here for plotting. And we are reading an input image, one of the input images that we have, and go ahead and predict it and plot right there. Pretty good job with 5 training images. And I did take about an hour for me to annotate because we have lots of classes, lots of objects, but that is an amazing job. As you can see, individual cells right here. If you think these two cells are kind of combined, I don't know, I can't tell. No, they're not combined. It uses the same color, but you can see that bounding box for this specific cell and this big bounding box for this cell with 94%. But if you think half of the cell is, let's go ahead and do that. Why not? I was about to say, let's change this to 0.8. Very aggressive. So you can see how the output looks like. And after that, let's go ahead and plot it. And we should see, I don't know, some objects dropped and you see this cell, how this region is not picked up as a cell, and things can be a bit weird, as you can see. It's not perfect right there. So this is very aggressive. So let's go back to 0.5. Yeah. So let's go back to 0.5 and go ahead and run this. And once this is done, again, let's go down and check the average precision and recall, what type of metrics. Because we have validation data as my data set val, now we can go ahead and check the evaluation. So this is Coco evaluator, and go ahead and print the inference on this data set. So just copy and paste these lines. You will see, let's see, what type of values do we get? I mean, obviously, I would love to see hundreds or 90s right there, but average precision right there, 41%, precision 50 percentile. Go ahead and look at what these mean in the documentation, but you can see about 50-60%, which is okay on this one. And for cell, average precision is 80.64, for Canalicular vessel 36.1. Alpha granule, the one that's called mitochondria, is the one that's bringing everything down, because we don't have enough annotations for mitochondria. If you remember, we only have a few, so it's also, on top of that, more challenging to segment mitochondria, because in some cases these annotations overlap with I believe alpha granules. But anyway, so 3.8 is too low, obviously. But on average, I mean, cells are easy. I'm getting 80%. So I love this output, because it gives you different types of metrics, and you can, based on the metrics, you can see what to adjust, and what to annotate more. Okay, so I think that's okay. That's what is this? What are we looking at now? Yeah, evaluation. So all of that is fine. So now let's say, okay, I have a good model, predict and save. Let me delete this. I was experimenting with something. I don't want to give you all my experimentation stuff. Okay, so predict and save the results. This part I was experimenting, I included that later. So much for being prepared. So load a new image and segment it. So the previous one, we already have like the image defined, and that's what we got, right? So if I come back here, this image, we are not loading it. This is something that we already have as part of our data set, so we are kind of testing it on one of the ones. Now let's go ahead and load a new image, an external image. So we have a bunch of images as part of our test. I'm just going to pick a random image, like test image number 3, and go ahead and read the image using cv2.imread, and our output is nothing but predictor on this new image. And then we are visualizing and plotting. So this is a absolutely completely new image, not part of our train or validation, and let's see how it actually works. So the cells are segmented perfectly. Alpha granules, it's doing an amazing job. And did it pick are there any mitochondria in this image? Mitochondria is so rare in this data set. It's tough to find it. But we can segment a whole bunch of images and see if we find any mitochondria in them. Yeah, that's the next part. Process multiple images in a directory and save the results in the output directory. So now I have the entire test directory, and I want to segment every image and put the results in the test results directory. So let's go ahead and run this, just for the fun of it. And that's going to be 50 images, because I have 50 images. As you see, it's cycling through. And while it's doing that, let's go ahead and open this to see how things are being populated here. 3D EM platelet, there should be test results, and the images are slowly showing up right here. Yeah, you see how it's adding more images. Let's just take a random image, download it, and have a quick look at it. Why not? And let's open the file. There you go. That's not bad, right? I mean, is there any mitochondria? Now I'm fixated on this mitochondria thing. I don't see anything visually. Maybe you can freeze the screen and have a critical eye. But, oh, there you go, mitochondria, that one. We caught one. So can I zoom in? Oh, there you go, that one. So it's rare, but it's actually getting these mitochondria. How many of those are correctly segmented? How many? Oh, there is another mitochondria right here, 75%. Okay, I'm okay. I'm happy with this. It'd be nice if we can color these each object in different colors, so it makes it easy. But anyway, so this step, let me go ahead and close this part. I think this step you understand. We are segmenting and saving these images, but I hate images like those, because they're not quantifiable. The whole reason why we are doing this for scientific images is we want to quantify them. What good is an image that you can, I mean, that's a great image, the one that I just showed you, to print and put it on your wall, showing that, hey, look how great my algorithm is, but we want quantification. So one way of doing that is segment images and save objects. So in this case, I want to, I'm going to use the scikit image region props to actually take the labeled images and then extract region parameters from that. I have covered that in many videos in the past. We have done that. So I'm not going to explain what exactly it is, but code is right here. So what we are trying to do is, okay, we have an input directory, text, test, take all the images one by one, And I'm also initiating here, creating a output file called output objects.csv that captures all the information about these objects. Now with that file open, go ahead and write what? First of all, add a first column called file name, class name, object number. So for each file, I'll have different classes, right? Mitochondria, cells, and so on. And then I have different objects. Within mitochondria, I have mitochondria 1, 2, 3, 4. And then what is the area of it? What is the centroid? What is the bounding box? All the typical stuff. Now open each file, go ahead and read the file, and go ahead and predict on it. Now get the mask out of it, because the mask is nothing but your instances, right? And convert that into a NumPy array, and convert that into a binary like Boolean, and then go ahead and get the labels, and now take the label masks and get the region props. Now you get the properties, and from the properties, go ahead and get area. You can add more properties if you want. I just picked area and a few things, and go ahead and add them to the CSV file. So this is a regular Python in action, and regular scikit image in action right there. So now it's loading each image, and it's actually, as you can see, it's cycling through. This is worth the wait. So I will actually, again, we are processing all 50 images. I should have selected only a handful of them, but no point. I'll pause the video, but let's look at the CSV file once it's done. Okay, so it is done, and we should see a CSV file. So let me go ahead and where did we save it? Is it in test results? I think we saved it in test results. Let's scroll all the way down. So output objects. So let's go ahead and download it and open the CSV file. I don't have Microsoft on this, Excel, but you can see how we have file name, class name, object number, area, centroid, bounding box. So this is the file name, for example, platelet19.png. So this is a cell. So how many cells do we expect in each image? 5, 6, 7. So there is cell number 1, 2, 3, 4, cell number 5. No, this is a carnicular vessel right there, and cell number 6, cell number 7, 8, 9, 10 cells in this image, in this specific image 19, but then you have all others. So this is everything that you want. Okay, so that is one way. And the other thing, we are good at Python, so why work with Excel and all other external programs? Why not just import that Excel file or CSV file that we just saved, and use pandas, and go ahead and use Seaborn, my favorite plotting library in Python, and go ahead and plot. So it depends on what questions you want to ask. One question I want to ask is, what's the average number of objects per image for each class? In each image, how many cells do I have, or how many mitochondria do I have, and so on. And also, what is the average area of these objects in each class? These are the only two questions I thought of asking, but obviously, depending on what else you want to do, go ahead and ask other questions, but there you go. So this is average number. I'm zoomed in, so it's tough to see. Zoomed in, so the code is easy for you to read, but you can see average number of objects, cells. We have about 11 cells per image, and when it comes to alpha granule, you have 20 plus in each image. Mitochondria, not many, 2 or 3 right there. Canalicular vessel, we have a lot of these, like 30 plus of these. And same thing with object areas. You would expect the cells to be pretty large, of course, and the granules are right there. Again, you can do your own violin plots and all that stuff. Now, finally, let's end this by saving the binary image, because, or you can call them multinary, because for each original image, I want to save a specific image for alpha granules, where each object is labeled 1, 2, 3, 4, 5, 6. Of only alpha granules. I'll have another image of only cells. So let's go ahead and run this. I'm not going to waste your time by talking and not running this here. But again, our output directory here is test results instance, and all I'm doing is just binarizing each of these instances and saving them. And that's the end of this. I'll actually talk about panoptic segmentation in a second. But I already talked about it in the last video. But all of this is done. This is so fast, because all we are doing is I'm actually surprised how fast this is. So let's go and see what happened here. I hope it worked. So test results instance right there. Oh, so all of this is done. Let's do one thing. I am going to download this and open this in ImageJ so you can see exactly how it's going to look like. So I am going back to my train. I am going back to my test results instance just to have a quick look. You see how I have, like, for this image, this is all the cells image. Anyway, it's not clear right here, so let's download this. Test results instance, download, and I'm going to pause this and continue as soon as this is downloaded and I have organized things in the background. Okay, so I just downloaded these images down here and I organized them into alpha Canalicular based on different classes. In fact, as you can see, if I go into these cells, there are 50 items because I have 50 images, and for each of those 50 images we have an image for cells. And if you open these cells image right here, you may not see much. You'll probably something going on faint right there, but the best way to actually open this is, for example, open this in ImageJ, a scientific program. Just a second, let me move this down here and adjust the brightness and contrast. But instead of single image, let's actually import image sequence. Oh God, I have this recording thing. Okay, so file, import image sequence and test result cells. Yeah, let's go ahead and import it, and you should see the imported image right away right here. Now let's go ahead and adjust the brightness contrast so you can see all the cells right there. You see how each of these cells apply to all 50 images. So how each of these, they have unique number, unique value right there. These are all the cells that are detected, and if in fact if I just go through this, you see how we have different cells right here. Yeah, that's pretty good. And now you can import. Similarly, you can import. Let's do one more, and then get back. What shall we look at? So let's look at mito. I don't know how many mitochondria we have, but let's see if it shows up fine. Adjust brightness and contrast, and let's adjust this to that point right there. Apply to everything, and there you go. Yeah, so you can see how we have these different mitochondria. Now, why would you need this? Now you can reconstruct this in 3D, and you can try to use another program that can give you 3D, morphologies if you want to extract those and all that stuff. So, but hopefully you appreciate how you can actually save these individual classes, individual images. So the whole point here is not just putting a fancy bounding box and showing color images. You're doing scientific images, which means you always are after some sort of a quantitative information, and that's exactly what you can get, whether it is in the CSV file captured as object measurements, or exporting them for further downstream analysis. Maybe you want to do some sort of a neighborhood analysis. Maybe you want to do, hey, segment this image, but within each of the segmented images, give me how many mitochondria are there and what is the average size distribution. Whatever you want to do in downstream, you should be able to do that. Okay, so that concludes how to train your own custom models. I think I added down here something called interested in panoptic segmentation. If you haven't watched my previous video, here is a quick summary of what panoptic segmentation is, which is nothing but, this is instant segmentation, right? So we are drawing a bounding box. Panoptic segmentation is nothing but segmenting the entire scene, which you'll see in a second, for every pixel. I am just showing this for the sake of completeness, but I do not have, I think what we have done up here with our cells is pretty much what is, at least the extent that I have used the Detectron2 model. So I hope, again, apologies for this long video, but I wanted to capture everything relevant to using your own, training data to training your models, and not just training the models, but also saving data, exporting, doing the measurements and all of that in one video. Otherwise, I don't want you to wait 2 more weeks for part 2 of this. So please keep asking questions as part of the comments, because that gives me ideas in terms of what else to test. And this is one of the ones where one of the commenters or subscribers actually asked about, hey, can we segment overlapping objects using unit? I'm like, I know with unit you cannot do that. It's not the right framework. But with Mascar CNN, of course, and by digging into it, I learned that Detectron2 does an amazing job. So if you have like any use cases where you have all these objects open, not just use case, actually with data, then I'd like to hear about how Detectron2 actually worked for you. Okay, let me not extend this any further. Please hit the subscribe button right now if you haven't already done so, and let's meet again in the next tutorial.